Okay, in this lecture we're going to cover the first part of our section 2.4 material on arc length and surface area. So in this first part of the section, we'll talk about how to determine the arc length of a function between 2 points. So to introduce this problem, let's consider the following. So here I say consider a smooth function, f of x, on the interval from a to b. And I ask, what is the length of the curve y equals f of x from the point A, f of a, to the point B, f of b? So let's try to visualize what we're interested in here. So suppose that we have in maybe the first quadrant of the xy plane the graph of some smooth function, y equals f of x. And I'm looking at the graph of this function on some interval from x equals a to x equals b. So when x is equal to a, this left end point of my curve would be the point where x is a, and then y, which is given by f of x, would be f of a. And this right-hand endpoint of my curve, when x is equal to b, would be the point where x is b, and y, which is f of x, would be f of b. So the question that we're asking is, what is the total length of this curve between those 2 points? So if we think about the graph of this function as maybe being a piece of string or something, and we were to stretch this string out into a straight line, what would be the length of that string? And this is known as the arc length of that curve between these 2 points. So let's see if we can introduce a formula for how to find this. So the idea is going to work as follows. Let's suppose that we take our interval from a to b, and I divide it up into little bitty sub-intervals that have an equal width, which I'm going to denote as dx. So here, the length of any one of these little intervals along the x-axis is what I'm going to call dx. So if I look at each of these x values that I chose when I divided up my AB interval, and I find the corresponding y values on the graph of my function by substituting these x values into the function, then the horizontal distance that I'm traveling between any of these points is dx. And the corresponding change in the y direction for these points is what I'm going to call a differential of y. It depends on what the function y is. So our vertical direction, let me maybe use a different color here. Well, that's fine. Let's call the corresponding change in the y direction dy. So if I know the change in the horizontal direction and the change in the vertical direction, dx and dy, then I can calculate the distance between each of these points on my curve by using the distance formula between points in the plane, or equivalently by using the Pythagorean theorem here. So if we think about one of these little segments, let's maybe pull out one of these expressions, or one of these shapes. We have a little triangle whose legs are length dx and dy, and we can see that they're forming right triangles. And so the distance between those points on my curve is going to be the hypotenuse of this triangle, and I'm going to denote this as ds. So the notation that we'll introduce here is that we'll call lowercase s the arc length of our curve. So this little segment of length along our curve would be a differential of the total arc length, or ds. So using the Pythagorean theorem, well, we can say that ds squared would be the sum of dx squared and dy squared. Or if I divide both sides of this equation by dx squared, I would have ds squared over dx squared is equal to dx squared over dx squared plus dy squared over dx squared. So what does this buy me? Well, the left-hand side of our equation is now ds dx quantity squared, which is equal to 1 plus dy dx squared. So taking the square root of both sides, we have ds dx is equal to the square root of 1 plus dy dx, or the derivative of y with respect to x squared. So finally, getting the differential of s, the differential of arc length, I would have the square root of 1 plus dy over dx, or the derivative of y with respect to x squared, times dx. So if I have an expression for the differential of arc length to get the total arc length along this curve from point A to point B, well, I want to add up these differentials of arc length. Those are these little green line segments along my curve from x equals A to x equals B. So that process of adding up these very small little sections of arc length along our curve is given by the definite integral of this differential for arc length from x equals A to x equals B. So what we've derived is the following formula for the arc length of the graph of a function y equals f of x. So here's what it says formally. If f of x is a smooth function over the interval from A to B, then the arc length of the portion of the graph of f of x from the point A f of A to the point B f of B is given by lowercase s, and it would be the integral from A to B of the square root of 1 plus, now remember in our formula we had dy over dx squared, which is just the derivative of y. So if y is given by a function f of x, then its derivative would be f prime of x. We're squaring that quantity, and then we had our differential of x on the end. Now I'll mention that you might see in some other textbooks or online videos, other people will sometimes use the notation capital L for arc length instead of s. So just be aware that there could be more than one notation. We might use L for arc length instead of lowercase s. It just depends on what textbook people use and what their own personal preference is for this notation. But we can use them interchangeably. So let's take a look at an example of calculating arc length now that we have a formula for the arc length of a curve. So here we're asked to find the length of the curve y equals 2x to the 3 halves from x equals 0 to 1. So here, our formula for arc length is given in the theorem, and one thing that we need to find is the derivative of the function which defines our curve. So just to stay consistent with notation here, let me give this function which defines my curve a name. I'm going to call it f of x, which in this problem is 2x to the 3/2 power. Now, to apply our formula for arc length, we need to find the derivative f prime of x, which would be, in this case, 3x to the 1/2 power, or equivalently 3 times the square root of x. So using our formula for the arc length of this curve, s, or capital L if you prefer, would be given by the definite integral over our x interval, which in this case was from 0 to 1, of the square root of 1 plus our derivative, which we found to be 3 square root of x squared with respect to x. So let's see what we have. We have the integral from 0 to 1, and simplifying under the radical, we will have a 1 plus, when we square 3 square root of x, we will have a 9x, and then our dx on the end. Now, to evaluate this definite integral, well, we see it involves a composite function, so we're going to have to make use of a substitution in order to find our antiderivative. So let's start by choosing a value of u. In this case, I would choose my inner function in the composition, which is 1 plus 9x, so that du would be given by 9 dx, or dx is equal to du over 9. Now, since our integral for arc length was a definite integral, we also need to change the limits of integration. So here, looking at our lower limit for the x integral, which was 0, we find the corresponding value for u, which is 1 plus 9x, would be 1. And for our upper limit of integration, which was x equals to 1, the corresponding value for u is 1 plus 9x, so we would have 10. So rewriting our integral for arc length in terms of u, we now have the integral from 1 to 10 of the square root of u, and then our dx term on the end we said is equal to du divided by 9, so that factor of 1/9 I'm going to bring out in front of my integral. So let's see what we have for our antiderivative now. We had a constant of 1/9 out in front, and the antiderivative of u to the 1/2 will be 2/3 u to the 3/2, and we're evaluating from 1 to 10. So in our last step, we can simplify the constants a little bit. We have a 1/9 times 2/3, which would be 2 over 27. And then when we evaluate this antiderivative, u to the 3/2 at u equals 10, well, we would have 10 to the 3/2, or recall that the 3/2 power is the same as, or for instance, u to the 3/2 power is the same as u times the square root of u. So if we have 10 to the 3/2, that would be the same as 10 times the square root of 10. And then we subtract the value we get when we substitute 1 in place of u. So 1 to the 3/2 power would be 1. So this would be the arc length of this curve over the indicated x interval from 0 to 1. So let's look at some other examples. This next example is sort of a typical problem in determining the arc length of a curve along a point. And it requires us to be a little bit clever in the way that we're going to simplify our integral for arc length. So here we're asked to find the length of the curve, y equals x to the 4th over 8 plus 1 over 4x squared from x equals 1 to 2. So as with the previous example, let me start by introducing some notation for this function, which is defining my curve. In this case, x to the 4th over 8 plus 1 over 4x squared. Or if you prefer, 1/8 x to the 4th power plus 1/4 x to the negative 2 power. Now, to apply our formula for the arc length of a curve, we need to find the derivative of this function. So here, f prime of x will be 4 over 8, or 1/2 x cubed, minus 2 over 4, or 1/2 x to the negative 3rd. Or if we rewrite this a little bit, we've got a 1/2 x cubed minus 1 over 2x cubed. So for our arc length formula, the arc length of this curve, S, is given by the integral over our x interval, which in this case was given as 1 to 2, of the square root of 1 plus the derivative of f, which we just found to be 1/2 x cubed minus 1 over 2 times x cubed squared. And then we're integrating with respect to x. So for this problem on arc length, along with some of the examples you might see in the homework or examples that we'll see later in this section, after you initially set up your integral to find the arc length, most of the time our goal is to simplify as much as possible under the radical. So that is, simplify whatever expression you have under the square root. So in this case, let's start by expanding the 1/2 x cubed minus 1 over 2x cubed squared. So under the radical, we had a constant 1, plus if we expand this factor squared, we're going to have a 1/4 x to the 6th power minus 1/4. So when we multiply our 1/2 x cubed times the negative 1 over 2x cubed, those x cubed factors will cancel. So we're left with 1/2 times negative 1/2, or negative 1/4. But we have 2 of those factors when we expand. So our minus 1/4 minus 1/4 will leave us with a minus 1/2. And then plus, for 1 over 2x cubed squared, we'll have a 1 over 4x to the 6th dx. So now, if I group my constant terms together, well, I have a 1 and a minus 1/2. So I now have the integral from 1 to 2 of the square root of 1 over 4x to the 6th. My 1/2, or excuse me, my 1 minus 1/2 leaves me with a positive 1/2. And then I've got a plus 1 over 4x to the 6th dx. So now notice, one thing that you might notice immediately is that the term that I'm left with here is exactly the same as the term that I had here above. However, the negative 1/2 is now a positive 1/2. So why is this helpful? Well, we saw that that term I had in the line above could be factored as 1/2 x cubed minus 1 over 2x cubed quantity squared. So if I just change the sign of that negative 1/2 to a positive 1/2, I can recognize that this expression under the radical can be factored as 1/2 x cubed plus 1 over 2x cubed, quantity squared, dx. So by recognizing that I have the same expression as in the previous line, but with a positive 1/2, I can see that I could factor it in the same way, but where my quantity that's being squared, instead of having a 1/2 x cubed minus 1 over 2x cubed, I've got a 1/2 x cubed plus 1 over 2x cubed. So this allows me to then simplify as the integral from 1 to 2, and the square root of this quantity squared leaves me with 1/2 x cubed plus 1 over 2 times x cubed dx. So let's see what we're left with for our antiderivative. The antiderivative of 1/2 x cubed will be 1/8 x to the 4th power, and the antiderivative of 1 over 2x cubed, or 1/2 x to the negative 3rd, would give me a 1/2 x to the negative 2 divided by negative 2. So altogether we'll have a negative 1 over 4 x squared, and we're evaluating this quantity from x equals 1 to x equals 2. So let's see what we're left with. When we evaluate at x equals 2, we would have 2 to the 4th, which is 16, times 1/8 gives me 2, minus 1 over 4 times 2 squared is going to be 1/16. And then I subtract the value I get when I evaluate at x equals 1, which would be 1/8 minus 1/4. So let's see what we're left with. To combine all of these terms might be helpful to get a common denominator of 16. So our 2 would be 32 over 16 minus 1 over 16. Then I'm subtracting, well, I had a 1/8, which would be 2 over 16 minus 1/4, or 4 over 16. So grouping our terms together, we have 32 minus 1, and then we're subtracting a negative 2, or adding 2. So altogether we're going to have 33 over 16 for the arc length of that curve between the indicated x values. So this is a pretty typical example of a problem in arc length where we need to simplify under the radical by maybe expanding our derivative terms squared and then grouping some like terms and factoring again in order to cancel that square root. So there's a few problems similar to this in that section 2.4 homework. So let's look at one last example for today's lecture. So this next theorem is going to be a formula for the arc length of a curve, which would be the graph of a function of y instead of a function of x. So let's consider the problem of interest. Suppose that we have in the xy plane, maybe in the first quadrant, some curve which may not be the graph of a function of x, but we could consider it as the graph of a function of y. Say x equals g of y. And our endpoints of this curve would correspond to values of y given by c and d. so that these points on the curve would have an x-coordinate, which is g of y, so g of c, c. And this upper point, when y is d, x would be g of y, or g of d, d. And we want the length of this graph between those endpoints. So using a similar approach to what we did when we derived our formula for arc length of a function of x, we arrive at the following theorem, which is an arc length for a curve which is a function of y. So here's what it says. If g of y is a smooth function over the y interval from c to d, then the arc length of the portion of the graph of g of y from the point g of c, c to the point g of d, d is given by s, which is the integral along the y interval from c to d of the square root of 1 plus the derivative of our function, so g prime of y squared with respect to y. Or again, in other textbooks or online videos, you might see the notation capital L for arc length instead of lowercase s. So just a matter of personal preference, which one you want to use. We can use them interchangeably. So in this last example, we're asked to find the length of the curve, x equals the natural log of cosine y, for y between 0 and pi over 4. So as with our previous examples, let's start by giving this function a name. So here the function which is defining my curve is g of y, which is the natural log of cosine y. And so we need to find the derivative of y. So by the chain rule, recall that the derivative of natural log of a function is given by a quotient where the numerator is the derivative of the inside function. So here the derivative of cosine y is negative sine y. And then we divide by the inside function, cosine y. So here we have negative sine y over cosine y, or we can simplify this as negative tangent of y. So once we have our derivative, we're ready to set up our integral for arc length. So here we would have the arc length of this curve S, or capital L, is the integral from, in this case, y was given as being between 0 and pi over 4. And the function that we're integrating is the square root of 1 plus the derivative of g, which we just found to be negative tangent y squared dy. So let's see what this gives us. We have the integral from 0 to pi over 4 of the square root of 1 plus tangent y squared dy. However, we can recall, using trig identities, that the sum of 1 plus tangent squared y is equal to secant squared y. So in this line of your work, you may want to make a little note. We have a trig identity that 1 plus tangent squared of any angle is the same as secant squared of that angle. So here we're just making use of that trig identity. So that allows us to then rewrite this as the integral from 0 to pi over 4 of secant y dy. Now recall from section 1.5, when we were talking about integration by substitution, we derived a formula for the antiderivative of secant. So recalling the formula that we had derived for the antiderivative of secant, we have the natural log of the absolute value of secant y plus tangent y. And then this antiderivative is being evaluated from y equals 0 to pi over 4. So you might want to make a note to yourself in your lecture notes that for this antiderivative, you might want to see section 1.5. So we had derived this formula for that antiderivative, and in the section 1.5 lecture, I had mentioned that you probably want to have this formula for the antiderivative of secant memorized. It will come up a few times throughout the course of the semester, so it's helpful to have it memorized. So in our last step, let's evaluate this antiderivative at the endpoints of our interval. Here we have the natural log of absolute value of secant pi over 4. Now secant, recall, is defined as 1 over cosine. Now cosine of pi over 4 is 1 over the square root of 2. So to get secant of that value, we would take the reciprocal, and we would have simply root 2. Plus tangent of pi over 4, which is 1. And then we subtract the value that we get by substituting 0 in for y. So we would have the natural log of absolute value secant 0. Now again, secant is the same as 1 over cosine. So we would have 1 over cosine of 0, which is 1. And then plus tangent of 0, which is 0. So we're left with the natural log of the square root of 2 plus 1. I don't really need the absolute value there because square root of 2 plus 1 is already a positive number. And then I'm subtracting the natural log of 1, but recall that the natural log of 1 is equal to 0. So all that we have is the natural log of square root of 2 plus 1, and this would be the arc length of the graph of the function that we're given on that y interval from 0 to pi over 4.